Great, recording is on. So what I'm going to start us off this week with just a very quick reminder of what we learned at the end of last week, or rather what we started to look at the end of last week was we were talking about Bayesian modeling and how you can, in a Bayesian framework, you can create these models where you have, say, one model that is designed, that says, I have a likelihood that takes a particular form, and I can create another model which has a likelihood in a different form. And then a natural question is for me to ask, which is the better model? Which model gives me a more, a higher posterior evidence? And so we went through this process and we came up with the way of constructing Bayesian hypothesis testing, which was by taking two models and comparing the posteriors of those two models. But then we let in with this idea, which was that there's always some uncertainty in specifying a particular model, in specifying a single model, a single likelihood. And one of the utilities of the Bayesian framework is that I can construct a single model that actually contains lots of different models. And so the example that we gave last week was, let's consider that we believe that our data has either a Weibull distribution or a gamma distribution. Now, the Weibull distribution follows this form. This proportion is a function of two parameters, beta and gamma, and it has this form. The exact form you don't obviously have to memorize. And the gamma function is a slightly different function, and it has two parameters, alpha and beta, and it takes this form here. Now, the reason that these two functions are interesting is because they both fall within the gamma family of distributions, and that family is a function of alpha, beta, gamma, and it takes this form at the top here, which means that instead of specifying one model and one other model, and then comparing the likelihood, the posterior evidence of those two models, instead, I can create one model which contains both of those distributions in it. And then instead of optimizing for beta and gamma, or rather, analyzing my data with beta and gamma as my free parameters, and then alpha and beta as my free parameters and comparing the posterior, instead I can just create one posterior which uses alpha, beta, and gamma together. And that by definition will contain this model and this model and a whole lot more. Now, it doesn't have to contain a whole lot more, because I can construct a likelihood that forces the general function up here to only be valid if alpha is equal to 1, which is the Weibull case, or if gamma is equal to 1, which is the two parameter gamma case, and it's 0 otherwise. And that essentially forces me back into the two model case, but I'm still only analyzing one posterior. And so it's a way of doing this all at once. The difference between doing it individually in two chunks and doing it all at once is that now I have to have these three things as free parameters. And that leads us to a concept whereby we have an unknown distribution that we want to analyze, a set of parameters that govern how that likelihood is created that sit above the likelihood model itself. And we use those hyperparameters to govern what the likelihood looks like. And this process is what's called Bayesian hierarchical modeling. And we're going to talk about that for about the first half of this lecture, hopefully not the full half, but we'll see. And then we're going to start talking about machine learning after that. So what we're going to do is we're going to start with just a Bayesian hierarchical model. It's going to be easier for us if we just start small, and we go through and we talk about how you can create a hierarchical model and what that entails. And so what we're going to do, this is from last week when I had to snip out this part, is we're going to take a pretty simple initial model and we're going to go through a couple of logical steps and demonstrate how we can create a much more complicated model. So the first data set we're going to look at is the data set. It's a data set from the US, and it's 8 high schools reporting their performance on what's called the SAT-V exams, the Scholastic Aptitude Test verbal exams. Now, under the assumption that all schools are independent, we can then randomize students and randomly assign them additional tuition, additional tutoring, and see whether that additional tutoring is beneficial or is not. Now, the SATs are designed specifically to be robust to short-term effort, so that you basically can't just work for a week and score very highly. However, every school thinks that they're smarter than the SATs and thinks that their program will get a big benefit for their students. There's no prior expectation that any program at one school is better than any other. And so this is our setup. We have 8 schools who have coaching, additional coaching prior to the SATs, and they report on the effect of that coaching. So we have J equals 8 independent experiments, and each of them is trying to measure a coaching effect, which we're calling theta J, subscript J for each of the schools. And it's being judged by NJ students, which we assume are independent and identically distributed observations, which each observation is Yij. So the Y observation is their score. The I is their school, the I is the person and the J is their school. And we assume that these distributions always have a known variance, just to simplify things. So that's a lot of words. What does that mean in practice? It means that the likelihood that we have is a very simple one. We have observations given some underlying coaching effect, which is a Gaussian that centers on the effect, centers on the amount of improvement that their coaching gives you with some scatter. And there are data points for each student and each school. Cool. The estimated effect of the coaching at each school is given by the mean of all of the student values at that school. Okay, so we just have some average linear math, arithmetic mean. Oh, my summation has died. We have some arithmetic mean, and it sums over Yij and is divided by Nj, which gives us our arithmetic mean. And we have some uncertainty on that mean, which is this is the standard uncertainty on the mean, and it's given by the variance of the distribution divided by the square root of n. Okay, rather standard deviation divided by the square root. So for each school, we have this distribution, this value of their effect, of their observed effect, given their belief or their underlying true effect, follows just this Gaussian distribution. Now, these are the data, okay? So these are our schools, A, B, C, D, E, F, G, H, okay? The effect that that school estimates, so their value of theta, or rather their value of Y bar, which they're using to assume theta, is for school A 28 with a standard error of 15, B is 8 with a standard error of 10, etc., etc. So these are the data. Now, the thing that we're interested in is asking the question, does the coaching help? Now, there's a whole bunch of ways that we can go about this. Now, the first way and the most simple way is to analyze each of these schools, each of these results as if they were totally independent. Okay, so we have completely independent values of theta J for each of the schools. That is to say that the coaching effect is actually independent depending on which program you're working in. So one school's program can be way, way better than another school's program. Okay. At first glance, when you look at each of these independently, these look like there is a very, very wide spread in the results. It looks like for school A, there's a very significant impact of their teaching. For some schools, there's an effect, but it's not very significant. And for other schools, it does nothing or actually hurts you a little bit, right? So there's quite clearly a lot of variance here, but there's also a large error on each one of these measurements, a large standard error on each one of these measurements. So it's difficult to justify or to get any sort of population information from these individual estimates given the widespread. That said, if you were to construct like a credible interval for each of these values, which is just the 95% bounds given by the error and the value, the overwhelming majority of them will overlap and will overlap quite considerably, right? And that then says, well, maybe they are actually drawn from the same underlying population, and what we're seeing here is just sampling variance. And so our second possible model might be that instead of using the independent thetas for all schools, we can just take one value of theta. And that is the true value of theta that works for every single school. And that's what goes into it. So all of the theta j's are actually equal to one value, call it theta. Okay, this value, this hypothesis allows us to take all of the observations from all of the schools, bring them all together into one value, y bar total, with one uncertainty, and that gives us our pooled estimate of y bar, our pooled average for the effect. So assuming that all experiments have the same effect and that they produce random independent IID observations from that underlying parent distribution, we can treat the 8 experiments as being drawn from the same population with known variances, and then we can just simply take the weighted mean of all of our values, where the weight here is the inverse variance on the data. So we basically just weight each of these values by the inverse variance, and that gives us our estimate for y bar. Now that estimate, when we do the pooling, gives us a value of 7.7 for our estimate of the effect with some uncertainty. And that uncertainty you can calculate as the sum of the inverse weights, and that uncertainty ends up being plus 16. So if you were to draw this, if you were to use your posterior inference, then in this pooled estimate, the estimate of the true effect, theta j, is a Gaussian which centers on 8 and has a standard deviation and has a variance of 17. Okay. We have 2 models. One which we took everything as being independent, and one in which we took the pooled estimate of everything together. And we get 2 different values of the possible parameter that we're interested in. Which of these seems reasonable? Take the case of school A. In our independent analysis, school A has an average theta of 28 and a variance of 15, right? But in the pooled analysis, the estimate of theta has to be 8 because it's the same for every school with an uncertainty of 4.07. Sorry, that should be square root 15. And so we have wildly different estimates of the result of the parameter that we're interested in. This is theta for school A, depending on whether or not we go down the route of having the pooled estimate or go down the route of having the totally independent estimates. The first one tells us that the probability of the true value of theta A, theta 1, being greater than 28 is 50%, because that's the mean. So the probability that the true coaching effect in school A is greater than 28%, 28 percentage points, an improvement of 28 percentage points, is greater than 50% in the independent analysis. But in the pooled analysis, it's the probability of seeing a value that's greater than 28 is essentially 0. okay? Conversely, you can go the other way. In the second experiment, the probability of seeing a value of theta that is -3 is 50%, right? Or, you know, it's not 95, it's not beyond the 95% confidence. And so essentially, it's very, very difficult to reconcile these two results. The problem is that both of these models nominally are equally justifiable. We have no idea whether or not all schools have no effect or all schools have differing effects that we should take into account. Given that situation, we can instead think about creating what we call the Bayesian hierarchical model for this setup. These two models that we've just been talking about, we can describe using something called a directed acyclic graph. Now, this is a really useful way of visualizing models. So we have some parameter, theta, and in this case, theta is independent for every experiment. So as you go from I is equal to 1 to n, or j in this case, you have an independent value of theta I, and that informs what you get out as your estimate with some noise. This is a non-hierarchical model with independent theta. The second model that we looked at was the pooled estimate. And the pooled estimate is also non-hierarchical, but it has a common value of theta. So theta sits outside of this little box containing our I indexes. Yeah. So what we observe, which is y bar I, is independent of the, uses independent thetas in the first case and uses a common theta in the second case. What about if we instead now assume that theta can vary? Theta can vary from school to school, but it varies because of noise. It's actually drawn from a true parent population, which has a mean that tells you the true effect of coaching. And then from that mean with true effect of coaching, you sample a particular value of theta I, and you then get an estimate for the school, and you use that to test your observation. And then you use that as your model. That situation is a hierarchical model. So instead, we assume that the values of theta j are drawn from some parent normal distribution, and it has hyperparameters mu and tau, or that should be tau, sorry. And this then is the hierarchical model. So we have, if I was to cover up this section here at the top, then I would look like I had the independent version, but instead I've got this hierarchical model. Doing this mathematically is really quite simple, because all you have to do to generate this hierarchical model, or rather the posterior for that particular parameter, or for those particular parameters, is that you draw your values of theta from this parent distribution, which is a normal distribution, and then you multiply together all of the different probabilities of observing theta j given the parent population. So you're iterating the parent variables. You're modifying the parent parameters, mu and tau. And then you ask the question, what is the likelihood of observing the thetas that I observed at each school given these parent populations? And that's then this marginalization over the parent distribution, which is this f of mu tau. This is the hierarchical model. So you can interpret this as saying that the theta j's are randomly drawn from a parent distribution and distributed to all the schools. The schools then run their test and they get some measurement y bar. Your question, or the thing that we want to know, is what is the value of mu? Because that's the true underlying net effect of coaching, agnostic to the noise that there is on the measurements, right? There are a couple of reasons why this model is superior to the two models that we looked at previously. One of them is that you might expect that model I just described to be more realistic, but let's ignore that for a second. The main reason this is a particularly useful model is because of tau. What happens when tau goes to zero, when tau equals zero? Well, when tau equals zero, this normal distribution becomes a delta function with zero width, and it centers on mu, which means that all of the thetas get assigned the value mu, and all of a sudden we have the pooled estimate. So the pooled estimate is a subset of this function. What about the independent estimate? Well, what happens if tau goes to infinity? Well, if tau goes to infinity, the values of theta j become independent of one another. Because if I know theta 1 and tau is infinitely broad, then knowing the location of theta 1 gives me no information about the location of any of the other thetas, because I'm taking a sample from a Gaussian that has infinite variance. I'm taking a sample from a uniform distribution, and when I observe one value from a uniform distribution, it doesn't tell me anything other than this value is possible, right? And so the independent estimate is also a subset of this model. And that means that you have both of these previous models present in this setup, and you can take the values of tau between those two limits of 0 and infinity, and what you end up getting is some mixture of the result that you would get with the pooled estimate and the result that you would get with the individual estimate. And we can actually see this happening. So if we take these data and I force tau to be a value, a couple of values, a range of values on the x-axis, and then I calculate the estimated value of theta given all of the schools, A through H, right? And given the value tau, then what I see is that at tau is effectively infinite, which is 40 plus, the value of theta converges on the separate estimates. At a value of 0, it converges on the pooled estimate. And the distribution in the middle is some mixture of the two. Now, why is this useful? The reason this is useful is because the true value of theta is probably somewhere in the middle here, right? And using this model, you can borrow strength, which means that you can leverage the fact that you have multiple observations from a distribution that has some true intrinsic scatter, that's the tau, and you can use it to get a better handle, an unbiased handle on the value of theta that you're interested in, or mu in this case. This is just showing that the standard deviations also vary in the same sort of way. They converge on the pool and the separate estimates in the limit of high tau. They converge on the pooled estimate in the limit of low tau. Okay, that might not have been super easy to follow. And so the last thing that we're going to do today is something that's a little bit lighter. We're going to go through and we're going to construct a hierarchical model from scratch. And we're going to do it one step at a time, using hopefully something that you can tangibly identify with and appreciate. So this is the scenario. You have two passions in life, one of which is statistics, and the other of which is watching dog videos on the internet. These passions were largely separated until one day when you discovered televised dog shows. So this is the dog show data set that we're going to be analyzing for the rest of this lecture, or for the rest of this section. After an extensive period of time watching dog shows, you realized there was a couple of trends emerging. Some dogs, like this little guy here, regardless of their level of training, seem to perform poorly compared to others. And from your extensive viewing of animals and dogs in these shows, from your background research into historical dogs, famous dogs from history, and from your dedicated study of the canine brain during its growth, you come to the conclusion that the reason that some breeds of dog perform poorer in these shows is because of distraction. It's because, not because they are necessarily less adept, it's because they get easily distracted by things like this little guy. So we therefore set up a simple statistical test. Our statistical test is that we observe the performance of 17 dogs in the show, which are either border collies or golden retrievers. Okay, border collies being these guys, golden retrievers being these guys. Each dog was monitored through 30 different tests, all of which are reaction-based. Okay, and the faster the reaction time, the better the score. We now need to build a model, and this is what we're going to do, build a model to determine whether or not there is a systematic difference between this population and this population. Okay, so that's what we're going to do. So what do we need to do to make this data set? Well, we're going to do this, and the reason we're going to go through this step by step is because I want you to appreciate how easy it is to logically create a model from your mind and convert it into a model that you would then use in a real life data set. So we can start by making some simplifying assumptions, usually a very good thing to do in these circumstances. We can assume that all dogs, regardless of breed, share some common uncertainty in their reaction time. So that is to say that if every single animal had the same mean reaction time, just because of environmental factors, there is a standard scatter in that measurement. And we call that scatter theta y, and that's the same for all animals. We say that all collies share the same reaction time, mu1 or mu. And we say that all retrievers have a common reaction time, but our model is that they are slower by some factor beta. So that is to say that the observed reaction times of our dogs is drawn from a Gaussian distribution with center mu, mean time mu, and scatter sigma squared y, if they're a border collie. And if they're a golden retriever, the observations are drawn from a slightly different Gaussian, which has some offset in the mean reaction time with the same scatter if they're a golden retriever. Now you can actually formulate this as a single probability using what we call an indicator variable S, which is just a 0 if it's a border collie, and it's a 1 if it's a golden retriever. Okay, and so that gives us the model that the observed reaction time given our suite of model parameters, which are these here, is a Gaussian distribution with mean mu plus SI beta, where SI is going to be 0 if it's a border collie, so it just turns into mu, and if it's a golden retriever, SI is equal to 1, and so you end up with this beta factor additionally. Same scatter in both. We can draw this model using a graph very, very easily. So our observations are Yij, so I being the dog, J being the experiment, so the one test of 1 out of 30 tests, and the observed reaction time of each pet is Yij. And that Yij is determined by whether or not it's a border collie, right? The true mean of the underlying reaction time distribution, the offset that we apply to the golden retrievers, and the uncertainty that's inherent to the measure. Is this a sensible model? Do you think that such a model would accurately capture all of the uncertainty, all of the complexity of the data set that we were just looking at? Well, let's think about, once again, let's think about a couple of the possible complexities. So one of these possible complexities is that we can remove the expectation that all dogs of a same breed will have the same reaction time. Instead, we can say that they have the same population reaction time, but that individual animals are drawn from a distribution which is governed by their species, right? Governed by their breed. And so what we can do is we can say that all breeds of dogs share a common parent distribution of reaction times, from which each dog itself has a reaction time that is randomly drawn. So that is that instead of now having the observations coming directly from mu plus SI beta, instead, we now have this new variable alpha. And alpha is the reaction time of that particular dog. And that is drawn from the parent population that's determined by the global mean and the delay factor if you're a golden retriever, plus some uncertainty that's driven by the width, by the uncertainty in a particular reaction time for a particular dog. With that value of alpha, we then draw the observed values of the reaction time, okay, from another Gaussian which hasn't changed. So that's as it was in the previous slide. So now we have a slightly more complex model where instead of the mu governing the observations, the mu now governs the individual dog's reaction time, and that governs the observations. Okay, but this is still a fairly simple model. And the thing that we have now, this is now a hierarchical model. Because instead of just having a suite of observation, a suite of variables that inform a particular value, we now have a parent distribution of variables that inform something within our likelihood that governs our observables. So we now have multiple levels and we've constructed a hierarchical model. Is this good enough? Well, cast your mind back now to the actual problem that we're talking about. The model that we've got currently says that if you are a golden retriever, you always have some delay with respect to the border collies in terms of your reaction time. And that reaction, modulo some scatter due to the fact that all dogs don't have the same reaction time, that alone explains the differences we see in reaction time. But this is clearly not a delay caused by some inherent genetic effect. This is distraction. This dog could have kept running, but didn't. And that factor isn't currently in our model, but we can add it into the model. Again, by making a simple statement. And that statement is that there exists some probability, lambda, that a particular dog will be distracted. And when they are distracted, their reaction time decreases, or rather increases, by a pathological amount, right? As you can see has happened here, okay? And you can formulate this by just taking a single draw from a binomial, so a 0 and a 1, to determine whether or not the dog was distracted, which is governed by the probability of being distracted, lambda. And then you have this tau, which is an unknown, which you want to then fit for as well. So our model becomes more complex, where we have, this is the same as last slide. We now have this indicator variable here that says, if you're a border collie, you never get distracted. But if you're a golden retriever, you get distracted with some probability lambda. And if you get distracted, then you have some catastrophic increase in your average reaction time, which is what this Gaussian is showing us here. And so this is our new hierarchical model, okay, where we have now the individual animal reaction times are governed by this branch. The distraction is governed by this branch here. And the final effect is your observation yi. Okay. That model is the final model that we consider, and it has a few important parameters that are relevant. The first of which is the delay, the genetic delay attributed to all golden retrievers. The second is the proportion of golden retrievers that are pathologically distracted in a certain fraction of occurrences, in any, the probability of them being pathologically distracted in any experiment. And tau is the delay that happens whenever they get pathologically distracted. Okay, those are the three variables that we're actually interested in. But notice that we've got all this other stuff in here, right? And that stuff comes essentially for free with this model, with this hierarchical model. We have the mu, which is the collie-parent distribution reaction time mean. We have the intrinsic scatter in measurements of reaction time, and we have the intrinsic scatter in the mean reaction time of a particular breed of dogs. And then we have these two indicator variables, which determine whether or not a dog is a collie and determines whether or not a retriever is distracted. So that's it. That's the whole model. Why did we go through this whole process? We started out with something, a model that was not dissimilar from this, which was there's a bunch of observations, yi, and they are governed by some parameter, which is the mean of the distribution of reaction times. And with two steps, golden retrievers have some genetic delay, and golden retrievers get pathologically distracted sometimes. We went from this model at the top to this model at the bottom. Coding this Bayesian hierarchical model up is essentially as easy as writing these in computer code, these 3 lines, to just an if statement and a couple of draws from a distribution. And then you can take whatever data set you've observed and you can run an actual analysis, a posterior. And in our case, if we run this posterior with a data set that we've observed, which I'm not showing you, we find that beta is equal to 3 seconds, lambda is equal to 50.55, and tau is equal to 15, which means that golden retrievers are intrinsically 3 seconds slower in reaction than border collies. But when they get distracted, they drop 15 seconds on their reaction time. And this happens 55% of the time. But they're still good dogs. So this is the hierarchical model. This is an example of the hierarchical model that we've been creating, and I think this is a nice demonstration of how quickly and how easily you can go from something that is objectively quite simple to something that is objectively very, very complicated. In a few steps. Now you can imagine applying the same sort of logic to whatever analysis you want. And this is where the kicker comes in. This process that I've just described to you is not actually from looking at the reaction time of dogs in a dog show. The exact process that I just took you through of taking a data set of reaction times and looking at possible genetic effects, possible effects that are related to environment, and possible effects that are related to intrinsic scatter and population differences and things like that. This model comes from the treatment of reaction delays in people who suffer from schizophrenia. It is exactly the same process. Obviously, the data set is slightly different, but the logic in how you take a simple model and develop it one step at a time in complexity is the basis of treatment of one of the most harmful, mental diseases that people can have. And this is fundamental. I mean, this is something that you should not underestimate the power of these models and how easy they are to get extremely good descriptive power over a complex data set. They are very, very powerful. So that's the Bayesian hierarchical model. I'm going to end there with the hierarchical models because I think we've spoken about them enough. I'm, of course, happy to give you other examples, give you other demonstrations and things if you would like after the course. But for now, I'm going to go on to the interesting thing for the remainder of the course, which is going to be machine learning. So I have a handful of slides here about machine learning, and these are very, like, they're not super complicated. They're not super deep. They're designed to give you an indication or a series of ideas of things to go about and look into, plus some demonstrations of what you can and can't do with machine learning, some warnings. I know that machine learning isn't technically a statistic, but I think that it does fold in the umbrella of useful tools, and that you will definitely use machine learning programs at some point in your academic careers, and so it makes sense for us to go through them. It's also important because this last point is related to statistics. So where these biases come from is very heavily related to statistics. Okay, so we're going to start by just talking about what is machine learning. There are three machine learning as a rule, or as a class of algorithms, are essentially algorithms that improve themselves over time by using their current state, the previous states, and the available data. Okay, so there are three main types of machine learning. They're what's called supervised learning, unsupervised learning, and reinforcement learning. We're going to go through what each of those is now. So supervised learning is a method for mapping some vectorized data set onto some scalar data set. What does that mean? It's basically regression. It's a way of taking an arbitrarily high dimension data set and mapping that high dimensional data set onto a particular one-dimensional data set of interest. So for example, if this is a multi-dimensional X axis, a vector of quantities of X, and I have some training data set shown as the black points here, then I can use supervised machine learning to regress a fit or a mapping from the parameters X, X tilde, onto the value of interest, which is my Y. So you can do this in linear regression. This is how random forests work. So if you're interested in machine learning classification, you can look at random forests, and also this thing called support vector machinery, SVM. It's also another place that supervised learning is very, very commonly used. I personally don't find supervised learning that interesting, but I do find the next thing very interesting. Unsupervised learning is a similar process, except there is no required output. So in your supervised learning, the goal of the machine is to produce the best possible mapping between some variables and some other scalar variable. In the unsupervised machine learning, there is no Y. There is nothing to map to. And so what the code does, what the machine does, is essentially try and explore the data set that it is presented with in as detailed a manner as possible. And there are a bunch of examples of how this is used. So one of which we're going to talk about is the self-organizing map. One of which is the principal component analysis, and the inverse of principal component analysis, which is the independent component analysis. To give you an indication of sort of an idea, just a very brief idea, unsupervised machine learning is essentially taking a data set X tilde. So here we're showing two of the variables, X1 and X2. And the unsupervised machine will basically try and extract as much population information from the various data that it is provided with. And this can be in terms of clustering or classification, like what I'm showing here. So the unsupervised machine will return that there are three groupings, three classes of this particular data set, one here, one here, and one here, as an example. And we're going to see more about what unsupervised machine learning can do in the SOM slide in a slide's time or so. The last method is reinforcement learning, and we're not going to talk about reinforcement learning a great deal, but reinforcement learning is essentially a combination of these two things. It's essentially a halfway between unsupervised machine learning, where the machine is trying to discover as much as it can about a data set, and supervised machine learning, where it is trying to map to some outcome. Now, the way in which reinforcement learning works is it essentially is presented with some amount of data, or it has some method for generating some amount of data, and then it uses some goal in order to determine whether or not its current setup is well constructed, is optimum or not. And the way in which I find this most intuitive to think about is one of the ways in which it is used, which is teaching computers how to do stuff, right? So like teaching a virtual computer how to stay on the road, for example, like you can see in this little GIF. Now, the computer is only presented with this information that's in the green box, right? And its goal is to stay in the lane. And so it basically creates a bunch of methods for how it's going to navigate this space. It creates what's called a policy for how it's going to navigate the space when provided with a particular input. And then it uses that particular policy to march forward through the data set until it gets to a point where you have a failure, essentially, which is it leaving the road. And then it goes, was this better or worse than my previous policy? And it updates the policy and goes again. And this is reinforcement learning. So it basically uses this method of repeating and modifying a policy given a particular data set in order to determine what I'm going to do. So that policy, for example, might be that if this yellow line is, nearing the middle of the map, turn right, right? That might be one of the policy steps. But of course, it doesn't have it written out like that. It has it written out in computer language, where it interprets different shades and different colors and things like that. Okay, so that's reinforcement learning. Let's talk about supervised machine learning for a second, or for a minute. Supervised machine learning is most well known for what are called artificial neural networks, ANN. Artificial neural networks are a method of machine learning that is based on biological networks, on biological systems, like what's in your head. And the idea is that you have a series of neurons, and those neurons link together, and they are able to modify, or rather to interpret data differently. Each neuron interprets data slightly differently, and it weighs the outputs of that interpretation, and it uses it to form some sort of a complex function, some sort of a thing. So each neuron is a pretty simple item. It just contains some inputs, and it has a single output. Okay, so a neuron is a very simple thing in basic terms. One of the important facts, or the important parts of ANNs, is that the output can be sent to multiple neurons, and indeed often is. And so the output of a single neuron is a weighted sum of all of the inputs, where the weights are given along different connections. So let's say that this is our vector of input variables, x1, x2, all the way through to xn. And our neural network is one neuron. Our one neuron neural network, which isn't really a network, but there you go, takes the observed x values and a series of weights that it assigns to each connection. So each arrow has its own weight. And those weights are then used to create a weighted sum of all of these x values. And then the weighted sum is passed through a function, and that function is called the activation function. So this thing f of a. So the activation is this weighted sum of all of the x values, and usually we then add some bias to the weighted sum. And the reason we do that is not super important for you to understand right now. We then take that activation and we multiply, we pass it through the activation function, which gives us our output. Okay, so this is what actually happens inside each neuron. And the trick behind neural networks is that you take you take a series of inputs and a lot or a bunch of neurons, and you use those neurons to create a whole bunch of different outputs that are then passed to different neurons again. And those final neurons then take these weighted, do the weighted sum of these outputs, pass them through an activation function, and give you your parameter y tilde 1, y tilde 2 in this circumstance for this network. And these are the things that you use to do whatever it is you're trying to do, be it your y values being the y values that you're trying to optimize to on the y-axis if you're just doing a regression. If it's a classification problem, then this can be the assignment of being, yes, this is a number 1, no, this is not the number 1, for example, right? And stuff like that. These diagrams are really useful for some people. I personally don't find them useful at all. And I think that the best way to get an idea of what is happening in a neural network is just to play with one. And this is where one of the best tools available to you is already constructed. This is called TensorFlow, or rather this suite of machine learning tools is called TensorFlow. It's available in Python and in R. And this setup that they have here is a way for you to play with neural networks really visually and trivially. So what the goal is here is to feed the neural network some parameters. So an X value and a Y value, for example, and to set up the network. So this is the network that we just had, where we have 2 inputs. Oh, do we have 2 inputs? Hold on. No, we had 3 inputs. Let's give it 3 inputs. So let's give it also the checkerboard. So we have 3 inputs. We have 4 neurons in the middle, and we have 2 output neurons. Oh no, we just want the output actually. Okay, and this is our regression, right? Now, the goal here is to create a mapping using the neural network that follows the training data, that has a yellow ring on the outside and a blue ring on the inside. Okay, given the setup that we have here. Now, what you can notice about the way in which this network proceeds is that each one of these connections has a different weight, and the different weight is shown by the thickness of the connection. Those weights dictate the type of thing that each neuron is sensitive to. So this neuron here combines the 3 inputs and gives us something that looks like this like on its side hourglass. Okay, this one is the inverse of that last thing. This is a sort of offset checkerboard, and this is another offset checkerboard. Now, this is the initial conditions. We've not done any training yet. We're not actually used any artificial neural network, artificial training yet, machine learning. What we're going to do is we're now going to set off the training. And we're going to let the network re-weight things. So basically what the network does is it takes the output, it compares the classification of the outputs to the test data, which are these things, the yellow and blue points, and then it gets some sort of a loss function. And that loss function is what's going to be graphed up here. So when the loss is high, the classification is bad. And what the neural network is going to do is it's going to take that information and it's going to tweak the weights that it uses. I'm actually going to add a hidden, going to add a hidden layer because that is closer to what we had, because these are just the outputs. And it's going to tweak these weights that go into each one of these things, which modifies what each neuron is actually sensitive to. That modified image then gets passed to the output nodes, and they then create the classification. Okay, so watch for the different colors, or the different thicknesses rather, of these different things, and for how these images change as the network trains, because that's showing you what these nodes are each sensitive to. So ready? Here we go. And so what you can see is that as the training proceeded, we very rapidly decreased the loss function, now down to almost perfect classification. Right? And what's happening is that the first set of nodes, first set of neurons, have created a weighting that is, different for each different subpart. And it basically says this neuron is sensitive to that shape, right? Is going to weight things by that shape. This one is the inverse of that. This neuron is the same sort of thing, but offset, and this neuron is the same sort of thing, but offset again. And what you can see is that the final output here is basically driven entirely by these two neurons, because it is saying, I'm going to take that neuron there, and I'm going to give it a large weight. I'm going to take that neuron there, I'm going to give it a large weight, and then I'm going to take the blue component from this neuron here and give it a little bit of a weight. Okay, so the orange components from these neurons and the blue component from this neuron, and what you end up with is our final map, which is a perfect representation of the data that we're interested in. What happens if instead of using this annulus and a circle, we make the data a little bit more complicated? Well, if we do exactly the same process, you see the loss function now is having a much more difficult time creating the pattern that we're interested in. See, there's still a considerable loss, and indeed the classification doesn't look a great deal like what we're interested in. You can notice that these still have particular shapes, and as the network continues, it's constantly modifying the thing that it's sensitive to, right? But it's still not doing terribly well. It's still improving over time, but it's having a difficult time. We have some options here. We can instead give the network more information. Okay, keeping the same number of nodes and giving the network more information. Okay, now you can see these are becoming much more complicated. These maps are becoming much more complex. And the result is that the loss function is dropping considerably. And you can kind of get an idea now of where this final shape is coming from each of these nodes. And when you look at the final classification, it's not too bad. It's doing all right. You have these, spiral patterns are there. There's obviously something not going quite right in some of the parts, but generally it's doing reasonably okay. How can we improve this? How can we make the network more flexible? Well, the way in which we make the network more flexible is by giving it more ways to combine the input data. And we do that by adding layers. And this is where the neural networks come into their own. So the outputs of this layer, the modified data, is then taken and used as a weight for the subsequent layers. And that gives the network more and more complexity to be able to work with in order to reach the final destination, which is the shape that we're interested in. Now, when we do this, we have much more complexity here, so the network travels a lot slower, but the optimization travels a lot slower. But we have a much more flexible network that's able to produce much more complex patterns, right? And these complex patterns are what are important to finally end up with a shape that we're interested in, okay? And so we're still, you can see now we've done sort of 600, 700 epochs of optimization, and we're sort of still not great, but we're not too bad. Let's add in now the full amount of information. Let's up the number of neurons, and let's see what happens. So we've increased the number of possible neurons, the number of possible ways that the network can combine the data, and we've given it more information to be able to actually construct the input shapes with. And so now we've basically given it, quite a lot of freedom. And what you can see is that after a relatively small number of epochs, we've produced this spiral pattern. We've produced a classification that's pretty close to the actual classification that we're interested in. And indeed, if we let it run for longer or we gave it more flexibility again, we can add more layers, we can add more neurons, then things rapidly become more and more complex. Now, the more complex you make the network, the more the longer it takes to run each optimization, to run each epoch. But again, you get more flexibility, which gives you more model descriptive power. Hopefully that makes sense. This is an excellent, excellent tool for learning about artificial neural networks. So I highly recommend it. It's present in the lecture notes. Please go and have a look at it if you're interested. I'm going to leave this running in the background, despite the protestations of my computer, and we will have a look at it in a few minutes' time. Okay. So that's the artificial neural network. The next thing that we're going to look at is the self-organizing map. Now, the self-organizing map is, as anyone who's actually worked with me or knows me will know, is one of my pet favorites, something that I use extensively in my own research. And what the self-organizing map is it's a form of manifold learning, a form of unsupervised machine learning that fits a two-dimensional manifold to an n-dimensional parameter space. So that is, it has some two-dimensional thing, which here is shown as this mesh, and it has in this case, a three-dimensional blob, which is a weird shape. And then it takes this manifold here, and it tries to wrap the space in the manifold as best as possible. And that's how you end up with the final mapping. And that's this thing here. What this means is that the SOM is really good for both dimensionality reduction, so taking a large data set and compressing that information into a lower dimensional data set, much like PCA. And it's also very useful for classification. It's very useful for finding pockets of data that look similar to other pockets of data in your large n-dimensional data set. We can do this. We can actually visualize this and show this really easily. And I'm going to show you this now using a simple data set that I've constructed. So the data set is a random data set, which is governed by a bunch of random parameters that I didn't pick. It contains some parameters that govern the shape of a Gaussian in the parameter space in 3D, and some offset so that the populations are randomly distributed somewhere in the parameter space. So if I plot these, and I'm just doing it for two populations at the moment. So if I plot these two populations, you have something like what I showed earlier. We have this two blobs, and we're trying to get an idea of how we can classify these two blobs in 3 dimensions, the data from these two blobs into two groups. And we can do this using the self-organizing map. So the first thing that we do is we just fit the SOM. And for this, I'm going to use a function that I wrote called cotrain, which does a self-organizing map training. The name it comes from Cohen. Cohen was the person who came up with the self-organizing map. And all I'm doing is I say I want to train a self-organizing map. I want to train it on the data DAT. I want it to train using the variables X, Y, and Z. And I want my manifold, my mesh, to be 41 by 41 elements in size. It's a two-dimensional mesh. Okay, so I do my training and I plot my manifold, and I plot the counts of the data in my manifold. Now, This is the number of objects, the number of sources in my data set that sit within each cell of my manifold. Now, this manifold I've trained using Pac-Man rules. For those of you who are too young for Pac-Man, that means that it's what's called a toroidal geometry. If you go out the top, you come in the bottom. If you go out the right, you come in the left, vice versa. So if you were to print this manifold out, roll it, and then twist it into a torus, that's the shape that this thing has. It's a toroidal manifold, which I much prefer to just say it follows Pac-Man rules. What's really useful or really interesting about this is that firstly, there are these black stripes. There are these areas of the manifold where there are no data. And presumably that's going to be the gap. That's going to be where the gap in the data set was that we saw. That's going to be this gap here in 3 dimensions, right? And because we've compressed 3 dimensions down into 2 dimensions, there's now 2 of these gaps, right? And essentially 1 pocket here is going to be 1 data set, and 1 pocket is going to be the other data set. That's our hypothesis. How can we test that hypothesis? Well, what we can do is we can take this manifold that we've just trained, which again, remember, we've taken some mesh, we've fit it to the data, except in our case, now if we look over here down on my little notepad, what we've essentially got is we have, one of our data sets sits here, one of our data sets sits here if we were just in 2 dimensions. And the manifold has created a mapping that covers this area and a manifold that covers this area, something like that. But then it has to be a single unit, has to be a single manifold. So this is actually connected through some disjoint gap, which might look like that. And these here are the empty cells. These are the cells that are black in this manifold. They're the gaps. But what I can do is I can take this manifold and I can paint it by the value of the X parameter and the Y parameter. Because remember, this map here that I'm showing is in the manifold space. So it's actually, the first cell is this cell here, then the second is this one, then third, then fourth, then fifth, then sixth, then seventh, then eighth, then ninth, then 10th, etc. Which means that if I now paint this by X and Y and Z, what I should see is that these values all have similar X values. These cells all have similar X values. These cells all have similar X values that are different from these X values, etc. And I can do that, and indeed that's what I see. So if I paint the SOM by these different X values, Y values, and Z values, I see that there are 2 populations. These are the sources that sit on the negative side of the axis, the blue ones. These are the sources that sit on the positive X side of the axis, the red ones. And you can see that there are similar trends in Z and Y. Why is this useful? Well, given that we now have this mechanism for creating groupings of data, we've essentially grouped our sources into one half, which is one pocket of our data, and another half, which is the other pocket. That's this section of the SOM and this section of the SOM. And so what I can do is I can then say, well, let me just actually create 2 groups. And the way that I do that is I use this little function, generate cogroups. And what that does is it goes to every cell in the SOM and it says which 2 cells are the closest together. And if it turns out that the 2 cells that are the closest together are, let me pull up my little note here, are these 2 cells here, then it merges them into one. And then it repeats the process. It says, okay, which 2 cells are the next 2 that are closest together? And it says, oh, okay, they're these 2. And that now gives me 3 groupings. 1, 2, well, actually, sorry, it gives me n minus 2 groupings because each cell is its own group at the moment. And then I have these 2, which are 2 sets of merged cells. And I basically repeat this process gradually combining more and more cells together, and then eventually these cells will group together into a bigger grouping, et cetera, et cetera, et cetera, until I am left with only 2 groups. Because I believe that there are 2 distinct populations in my data set. And that grouping then looks like, so that process goes ahead and I group the data together in that way, and I color the SOM by which group the cells belong to, and I find that these are the 2 groups. So I have one group of data that sits in the blue areas, again, because it's Pac-Man rules, it wraps around, and I have one set of data that sit in the red area. So if I then use these 2 groupings and say, how well do these 2 sets of groupings actually satisfy, or rather recover, the true different populations in my data set, what I find is that the first chunk of data from my data set, which is, say, this one here, is recovered with perfect accuracy. So I get all 1,000 of my my sources from one cloud get assigned to one group, and my other group is almost perfectly assigned. There's a few sources that have scattered into the wrong group, but it's basically perfect. Okay. That said, we didn't really make the problem very difficult for ourselves, because, I mean, just looking at this data, I could probably go through and by hand and say, yeah, well, I'm going to just do a cut in the XY plane and in the XZ plane, and that's going to give me something that's roughly equivalent to the 2 populations. I mean, it wouldn't be terribly difficult to do that sort of a cut. Why does the SOM therefore have use? Well, the reason is because we made this easy on ourselves and we used 3-dimensional data, which is very easy for us to handle, very easy for us to visualize. But there's no reason we have to make it easy on ourselves. We can instead use some 4-dimensional data set, which is very, very difficult for us to visualize. We can make 10 discrete populations of our data set, which are all intermixed in various ways in our n dimensions. And we end up with something that looks like this. Now, I would challenge anyone to at least rapidly come up with good, discrete associations of all of these different things in 4 dimensions. I think that would be very difficult to do, especially by hand. But fortunately, this is something that we can do in the SOM with literally 2 lines of code. So we can take this 4-dimensional data set and we can assign 10 clusters, and we can basically go ahead with that process. So again, we just train our SOM. This time we're training on the additional variable W, keeping the same size. And you can see I've trained this data set in 4 seconds. I plot the counts, and now you can see that I've got even more breaks because I've got more distinct groups in the data, but also that there is some mixing going because the breaks aren't all totally clean anymore. If I paint the SOM by the components, then I get this. Again, much more complex than what we had last time. Still, these are only Gaussian observations despite being in 4 dimensions. So it's still a fairly well-behaved SOM. And once again, I can generate my groups, and I can say I want to generate 10 groups this time instead of the 2 that we had last time. And I can plot the location of those groups just like I did last time, and I get this here. So you can see that there is, one group which is assigned to group 10 here. There's a group 6 here actually bridges part of this 2-dimensional plane, which means that these cells here, these ones, one second, these cells here, no drawing. These cells here are actually closer to these cells here than they are to the red ones that are in between them, because this is a 4-dimensional topology that we have then squashed down into 2 dimensions. And so you end up with these jumps in the 2-dimensional space. But in reality, these objects are actually closer to these objects than they are to the red ones. It's an interesting thing to recognize. We can then use this manifold, we can then use this classification to calculate the ability of us to classify sources into their actual groupings that they came from. Now, if this was created with a sensible classification, then you would have A, B, B, C, C, D, D, etc., etc. But the way in which the SOM determines which things fall into group A, which things fall into group B, or whatever, is totally arbitrary, because there isn't it's an unsupervised method. There isn't a classification that it knows about that it's trying to optimize. Okay, so what happens is it's just the prediction just happens in an arbitrary order. The important question is, do the predicted objects all fall into one grouping, which means that they have correctly been identified as one discrete group of data. Okay, so we can basically go down the reference axis and ask the question, how many objects were assigned to a particular group from that reference? And you see that, okay, A was assigned to group I. Good. But B was also assigned to group I. Less good. So what's happened is that this big red section actually encompasses multiple true groups of the data. And so we've ended up assigning A, B, C all to I, but then we have D and E have both gone into F, so it's happened again. J has been assigned uniquely to F, so we have 100% fidelity. There's 600 sources per population, FYI. So F has been uniquely identified. G has been uniquely identified with some contamination. H has been uniquely identified, well, almost uniquely identified. I has been uniquely identified. E has been almost uniquely identified, and but has been split between the D and the E groups, and the F group. So why has this happened? Why has this splitting happened? Well, that's because if we go back here, you can look and see that some of these groupings actually sit along the boundaries of other groupings. And so realistically, what this is telling us is that if we wanted to do this sort of a split with higher fidelity, what we should probably do is fragment the data further, fragment into more than 10 groupings, and have some sort of a trash bin, have some sort of a, I don't know, these are ambiguous, but these populations are very well defined. Or you can keep it like it is and work with big, conglomerations of data. The point is that what took us 4 seconds to do would take us, a year by hand. So it's very, very useful, very, very powerful. Okay, that's the self-organizing map. The last thing we're going to talk about today is biases in machine learning. And this is the most important part of this section. Machine learning is very, very popular at the moment. And it is almost guaranteed that you will run into machine learning during your academic careers or even during your careers outside of academia. There are 2 serious problems with machine learning methods that I think you should know before you start doing anything with machine learning. The first of which is to do with extrapolation, and the second of which is to do with what's called covariate shift. The first point, extrapolation, is simply this: machines cannot extrapolate. And I use that very clearly. If anyone wants to have that debate with me, I'm more than happy to have it. But I don't think there is any argument that will convince me that you can construct a machine learning algorithm that will be able to extrapolate. They don't exist. And the reason that they don't work is because the fundamental premise of machine learning is to try and create a mapping that is as complex as the data allows where you have training data. But in order to do that, there's no limitation of what the model can do beyond the data, beyond the training set. And you can see that really simply from this particular example, where they've used a structure which has, you know, one variable trained on 10 nodes, trained back to one variable, regress back to one variable. And the training data sit in this region here, shown by these bullet points at the bottom. And you can see that in that regime, the data, the model, the neural network has done an excellent job of assigning the response of the network to the data. But depending on how many times you run the code, you get wildly different extrapolations out here in the wings. Wildly different. This is true of every network that will be trained, because when you do not have training data, you fundamentally cannot constrain what the network's behavior is. And the way in which I'm going to show you this is I'm going to go back to our panel here, and I'm going to show you this. So let's now stop. This has now been running on a fairly, a relatively simple data set for 10 minutes and has converged to pretty much a steady state solution, which is what you can see by the loss function not changing, right? I want you now to focus on what the data set, what the model is doing outside of the data set. So yes, the model is a very good match to the classification of the data set where there is data. But where there is not data, like out here, for instance, the model is completely wrong. Now, if I gave you a pen and said, sit down here and draw for me an extrapolation of this data set, you would do the obvious thing of drawing the following, I would imagine. Right, where your blue would continue circling around and it would continue going outwards. And similarly, your orange would continue circling inside and the spiral would continue. Okay, I think that's a pretty non-contentious extrapolation. That extrapolation, what you have come up with, is completely different to what the model has come up with. And that's because if there's no information for it to project on, the neural network cannot do it. It cannot extrapolate. Okay. And this is a serious, serious thing that you need to understand before you start doing neural network modeling. Indeed, extrapolation as a general rule is a bad idea. If you're extrapolating significantly beyond, or even a little bit beyond your data set, that's generally a very bad idea, statistically speaking. Okay. But for machine learning, it's particularly bad. So if you ever see someone using a machine learning algorithm and applying that machine learning algorithm to data that exists beyond where it was trained, they are doing something wrong. Call them out on it. Good. The next thing is also is a slightly more subtle thing, and that's to do with what's called covariate shift. And this is what we're going to finish on today. Covariate shift is the existence of a difference, a fundamental difference between the data set that you are using to train and the data set that you are using to evaluate or test your network. What does that mean? Well, let's go to my little notepad here and I can show you what that means. Let's say that we have our self-organizing map. Let's go back to our SOM here. So let's take our self-organizing map. And let's say that there is, we go to a particular part of our map. Let's say, let's do this. Okay, so let's go to a particular part of our map. Let's say this area here, the top here. Okay, and what we're going to do is we're going to ask the question, what does a fourth parameter, call it A, have in that population, in that part of the SOM? Okay, so we have our SOM, and our SOM, we go to a particular patch of it, which is over here. And in the train, this was trained on X, Y, and Z exclusively. The data set contains a fourth parameter that we are interested in, and that fourth parameter is A. In the test data set, the thing that was used, sorry, the training data set, the value of A in this part of the parameter space looks like this. And we then want to use the association of a second data set for which we only know X, Y, and Z to try and infer the properties of A for an unknown data set. Now, you can think about this if you're an astronomer as being, for example, galaxy colors as X, Y, and Z, or as being, for each of these, so X, Y, Z, or as being a, and then this parameter here, A, as being an additional parameter like, I don't know, redshift, distance to that galaxy. So we're using this as a mechanism for estimating the distance to galaxies, okay? The problem that we run into with covariate shift is when the population properties of this sample, of this upper sample that we use for the training, is different to the population properties of the sample that we're trying to use to infer. And so, for example, if the distribution of A in the test sample, so we'll call this sample T2 and this sample T1. So if this is T2, and then we have T1, second, and T1 looks like this, then we're going to get our value of A pathologically wrong for our inference if we use T2 to infer the properties of T1, right? Because what we do is we take our data set for which we know A, which is the black curve, and we assume that that is the same as the distribution of A for the second data set within this part of the parameter space. And that assumption pathologically is pathologically violated. Now, this is a really pathological example. We can construct a really simple way that this happens, which is like if we have a regression. So let me just make a simple regression. So I have instead a training data set that I want to train a regression on. And my training set looks like this. Okay, so that's my training set. And the black line is my regression, which has some extrapolation. I now have a test data set, which looks like this. So similar in this part of the parameter space, but then different in this part of the parameter space. If I then use this particular regression to estimate the value of Y given a value of X, I'm going to get it pathologically wrong. And that difference there between the two data sets is what's known as covariate shift. And it happens in heaps of data sets. Basically, whenever you have a difference between the selection that was used for one data set and another, in a machine learning method particularly, this problem rears its head. And the problem is that that difference is almost by definition present in every machine learning analysis. And the reason is because the training sample is never a representative sample of the thing that you're trying to analyze. If it was, you wouldn't need to do half of the work that you're doing. You would just work with a sparse sample. Okay. So this last point is a much more nuanced point, but it's very, very important. So I highly recommend that you go and have a look at covariate shift. Go and have a look at data set drift. These are two words, two things roughly for the same thing. And before you go through any machine learning exercise, make sure that one, you understand the differences between the training and test data set, because they will pathologically bias your conclusions. And two, make sure that under no circumstances do you extrapolate beyond the data set for which you've actually analyzed. Those are the two biggest gotchas. There are others, but I think those are the two important ones. So I'm going to leave that there. Thanks for staying on. I know we're a little bit over time. Apologies for that. I hope that that's been useful. That's the end of the machine learning part of the course. I'm not going to go through any deeper into machine learning unless people specifically ask me stuff. Next week, we have nominally our last lecture. However, I think that lecture would best be served as a essentially discussion session Q&A. So I will give the syllabus and the detailed agenda of what's on what's examinable to those of you who are taking the exam, and also if others are interested. And then next week, I'll set off a Slido this week, and I'll send it around on Moodle, and we can do essentially another discussion session like we had for the Bayesian statistics lecture. So please get your questions in on Slido of anything in the course that you would like more information on, anything in the course that you thought you didn't fully understand, you would like to have a recap on, anything that is particularly relevant to you and you just want to learn about it a bit more or have another reminder, anything like that. Then next week we'll meet for an hour and a half and we'll have a discussion session and go through all the things that you want to discuss about the course that you maybe didn't understand. Okay, hopefully that's a good plan for everyone. Thank you very much for everybody for coming today and for coming indeed to all the lectures. And once again, thank you for the evaluations. That was really, really great. That's all for today. So I guess I'll see you all next week. Keep your eye out on your inbox for an email from me about the new Slido.
Thanks, bye.